Okay, question 5 is a question that is related to the mains power. So we'll be using things like RMS values and P equals IV, all that wonderful stuff. Okay, so an electric oven is connected to 230 volts. Root mean squared main supply using a cable of negligible resistance. Calculate the peak-to-peak voltage of this mains supply. So, peak voltage is equal to root 2 times V RMS. Okay, which is root 2 times 230. Which is 325 volts. But it is asking for peak to peak, so I have to double that. So 650 volts peak to peak. Okay. Okay, so the resistance of the heating element in the oven at its working temperature is 12 ohms. Calculate the power dissipated by the heating element in the oven. Give your answer to an appropriate number of significant figures. So for this, we have to use our RMS values, not our peak values. Okay, and we're going to use the formula. P equals V squared over R. So that's 230 squared divided by 12. 230, oh, not 200. 230 squared divided by 12. And correct number of significant figures. I've got 2 significant figures. So that's 4,400 watts. Okay. Question B. In practice, the resistance of the cables connecting the oven to the mains power supply is not negligible. Each of the 2 wires connecting the heating element to the mains supply has a length of 3.15 meters. Each meter of wire has a resistance of 0.0150 ohms. So one thing I'm noting, I've got 3 significant figures there. Explain why the RMS voltage across the heating element in the oven will be less than 230 volts. Well, that's because you will have the wires have some resistance. So some potential is used in the wires because of the fact that V equals IR. Okay, you might also want to talk about something like the fact that basically because you have 2 resistors in series, it's a potential divider. that your actual potential in the heating element will be 230 minus this V equals I times R. Little things like that. So calculate the RMS voltage across the heating element in the oven when it is at working temperature. So what you have to pay attention to is the fact that the two wires are 3.15 meters. So you actually have 6.3 meters. Okay. And the resistance of the wire is equal to 6.30. Okay. That's double our length. Okay. Times the resistance per unit length, which was given to us here. So that's times 0.0150. So that is 6.3 times 0.0150. So that's 0.0945 ohms. Okay. I can use any of my formulas from DC circuits with AC circuits as long as I'm using an RMS value. So I'm going to use my potential divider equation. Okay. And basically, so my voltage for my element, okay, is going to be my VRMS times the resistance of my heating element divided by the resistance of the wire plus the resistance of the element. So this is the potential divider equation. Okay, and then I go, so 230 times 12 divided by 12 plus 0.0945, which equals and I've got three significant figures, so 228 volts. Okay, so this question here synoptically links back to section 4, the second chapter in section 4, which covers the potential divider. Okay, calculate the average power wasted in the cable due to the heating effect of the electric current. So, again, what I would look at is the fact that I've got two lost volts. Okay, so 230 minus 228 is 2 volts. So I got 2 lost volts. So my power lost is equal to V squared for R. And since this is in my cable, I got to use the cable resistance. So 2 squared divided by what I have as my resistance, 0.90945. Is 42.3 watts. Okay, so two reasons why it's important that the cable has a low resistance. One is a high resistance it could excessively heat up. Okay, and number two, you could if you got a high resistance, oh man, my handwriting is just as bad on an iPad as it is in real life. So you could lose too much potential, and it will cost you more. Okay, because you need to be operating at a certain amount of a certain potential, and you will get that potential. You will just draw more current, and it will cost you more money. So efficiency is key. So statements along that. So that's question